Then we are going to first do a course summary and then talk about a new chapter, which is about quantum machine learning. So let's see how far the journey we have gone so far. So we talk about tiny ML, efficient deep learning computing, deploy these powerful machine learning algorithms on resource-constrained devices, and also we did a project deploying Llama 2.7b on a laptop. So these are some of the stuff we discussed. This is a visual language model on a laptop. This is a tiny chat computer. This is a tiny ML on a microcontroller. This is BV Fusion, multi-sensor fusion on a JSON Orin board. So we covered from efficient inference with pruning, quantization, neural architecture search, distillation, and then we talk about efficient training, how to parallelize distributed training, on-device training, and also gradient compression, federated learning. Finally, we talk about application-specific optimizations from large language models to visual language models to diffusion models to point cloud to video understanding. So the principle is we want to open up the stack. We want to do full stack design to make AI more efficient across both the systems and also the algorithms. With such co-design, we can open a much larger design space and do the more optimizations. So this course basically covers knowledge from EE to CS to AI plus D. It's a interdisciplinary subject. So these are the three chapters we learned about from inference, remember about pruning, quantization, what we used in efficient computing these days, neural architecture search, we have a lab for that, knowledge distillation, teacher student model. For training part, we talk about different training parallelization strategies. We talk about data parallel, FSDP, tensor parallel, pipeline parallel, and also the sequence parallel. On-device training, and also tiny training engine on microcontrollers. And in particular, for application side, we talk about large language models, long context, post-training. We talk about diffusion models for image generation, video generation, and also using autoregressive approach, non-diffusion approach to do token in, token out generation, and also autonomous driving for with point cloud applications. We completed 5+1 labs from pruning to quantization to NISQ to LLM quantization and also LLM deployment. So we are growing. We have doubled the registration compared with last year and tripled across the year before. So across these 3 years, actually 8 times larger is our class. And the number of views on YouTube also more than doubled from 2022 to 2023. All right, with that, that's pretty much the course summary. And for the rest of this lecture, we are going to talk about advanced topics about quantum machine learning. So we have heard about quantum computing for a long time. It's a very hot topic. And what exactly is that? What's the foundation of that? And how is that applied to machine learning? And what is the state of the art? And how far away are we from quantum machine learning? So we have an expert, Dr. Hanrui Wang, who will who just graduated from our lab this year and will be an assistant professor in UCLA next year. So let's welcome Hanrui to talk about quantum machine learning.
Okay, thank you, Professor Han, for the kind introduction. Thanks everyone for coming. So my name is Hanrui Wang, so I'm an incoming assistant professor at UCLA CS, and I just graduated from MIT this year. So I'm going to talk about something about the intersection of the machine learning and also quantum computing, the two buzzwords nowadays. So you must heard a lot about the recent advance in the quantum computing. Actually, yesterday, the alpha qubit was released from Google's team. So basically, they try to use some advanced AI models, the transformer models, to decode the quantum error correction code. So, and also several years ago, the Google quantum team also have the quantum supremacy demonstrated, which means that the quantum is available, can perform better. Quantum can have a better performance compared to the best classical computers. And also IBM, they're also a big player in the field. they have this quantum utility demonstrated, which means you can do some computation on a quantum device, which is very difficult on a classical computer. But maybe not generating some real values, because those computations may not be very useful. But at least for those computations, it's very difficult to perform on the classical ones, and we are trying to find some useful applications for them. So in this today's lecture, I will going to just give a very brief introduction of the basics of the quantum computing, from what is the qubits, quantum bit, and also how can we perform different gates, how to operate those qubits, how to apply different computations on the qubits. And also we are going to introduce quantum circuit, which is the basic building block for the quantum program, which means you can have a bunch of qubits and also some quantum gates to manipulate the states of the quantum bits. And also we are going to introduce the current era, which is the noisy intermediate scale quantum era, or called NISQ, which means we are still pretty at the early stage where we have a lot of noise and also not large number of qubits available. And finally, we also introduce some example workflow to compile a basic quantum machine learning circuit to the available quantum devices, especially for the superconducting and also the neutral atom quantum devices. So here is a figure showing the number of qubits that is fabricated in the recent 10 years. So back to 2017, we have 5 qubits on the superconducting chip, which is shown on the left side. And we are placing those chips in the refrigerator, which is called dilution fridge, which is like a large chandelier on the roof of a room. And then basically the temperature of the inside this big fridge is going lower and lower as we're going down to the layers, and all the way down to several millikelvin, which is very close to the absolute zero temperature. So in that case, the qubits will have some superconducting effect, and the energy will have discrete levels, so we can represent information in 0 or 1 degrees. And after that, we also take several years for the scientists to further advance this field to build a larger and larger qubits. For example, back to 2019, we have 27 qubits, and also in 2020, we have 65 qubits. And last year, actually, IBM released this Condor chip, which has over 1,000 qubits. And on the bottom side, we also see a lot of demonstration on the error correction side, which means we not only care about the size of the qubit chip, but also we care about the quality, right? So because even if we have a large number of qubits, for example, in terms of the machine learning scenario, you may have 10,000 GPUs or even 100,000 GPUs, but how to fully utilize them is a large problem. That's also the case for quantum. So now we have 1,000 qubits, but for many cases, we cannot fully utilize the computing power within those 1,000 qubits because of the large noise. When you have use all the qubits all together, the final results will be very noisy, and the correct answer cannot be retrieved from the computer. So in that case, many of the recent advancement also goes to the logical quantum qubits, which leverage the error correction code. On the bottom side, we can see around like 48 of the logical qubits demonstrated on the neutral atom device at Harvard, and they try to leverage. The basic idea is that you can add more redundancy for each qubit. So say we can have 25 qubits, physical qubits, to represent 1 logical qubit. And in that case, we can tolerate a larger amount of the errors and still obtain the correct answer. So for the fabrication of the quantum device, unlike the classical device, we are all using the CMOS, the semiconductor technology roadmap. Actually, for the quantum device, there are many different technology roadmap which differs significantly to each other. For example, in the superconducting, they are fabricating the artificial chip with the superconducting transmon devices, hardware device, and the qubits are fabricated, are artificial ones, are not the natural ones. So the first, you can see the IBM on the left, the most side, which has over 1,000 qubits, and also Google, the second one is from Google Sycamore machine, they have 53 qubits. And also there are other technologies like the trap ion, so we can use the ions as the qubits to control the states of the ion. And also we can have a neutral atom device where we use the charged neutral atoms as the qubits, and we can use the laser to control the states of those items. And besides those, we also have the other roadmaps such as the photonics quantum device and also some of the others like the semiconductor-based quantum device based on the spin qubits. So in the recent years, as we see the number of qubits actually increase exponentially. So we can see it actually doubles every year in terms of the number of qubits. And also the computing power inside those qubits actually also increase exponentially with the number of qubits. The reason of that we'll introduce later, but intuitively when you have more qubits, it's not like in the bit. You have one more bit, you have just one more bit of information. But if you have one more qubits, the size of the vector, the size of the information you can represent with one more qubits is actually doubled. So we can imagine the computing power also increase exponentially with the available number of qubits. So that's increased, the computing power actually increased with this double exponential rate. How can we leverage this large space? So we know that every day we are generating around 3 exabytes of the information from all over the world. And actually we can just represent all of those information with only 64 qubits because we have 2 to the power of 64 of the length of the state vector that we can use inside those 64 qubits. So if we have a 100 qubits machine, and then the size of the information we can store inside those 100 qubits is actually pretty huge, which is 10 to the power of 30 bit of information. So that is equivalent to 1 billion years of the information generated by all the human beings at the current rate. So you can imagine that we have this large space and we have the enormous power to control those qubits. But in order to obtain some meaningful results or execute some of the meaningful algorithm, we still need to carefully manipulate those states and also design specific algorithms for the quantum device. So the history of the development of the quantum algorithm can be separated to multiple stages. Back to 1980 to 1990s, people are actually developing a lot of novel quantum algorithms. So actually one of the pioneer of the quantum algorithm, Professor Peter Shor, is also a professor here at MIT, and he developed the factoring algorithm, which is a famous algorithm to find the integer number, the prime factors for large integer numbers. So as we know, actually for the encryption domain, so we are using the RSA algorithm. So the fundamental foundation for the RSA is that it is very difficult for the classical computers to find the factors of large integer numbers. It is easy to compute the product of 2 large integer numbers, but once you have the large integer number, you cannot easily find what are the 2 original numbers to start with. So in that case, quantum device actually provide, there is an algorithm called a Shor's algorithm to do this with exponentially speed up compared to the classical ones. So you can imagine that's a very huge impact. So actually back to 2018, there is a national quantum initiative started by the US government trying to replace all of the this vulnerable RSA algorithm to the quantum safe protocol. So recently from the NISQ, they have already narrowed down the encryption algorithm to only 4. So in that case, in the future, if there's hopefully no new quantum algorithm cracking those encryption schemes, protocols, and then we can switch to those quantum safe ones. So back to the 1980s, people are very excited about this quantum algorithm because for the first time you can do something that is very difficult on the classical, but with exponential speed up on the quantum. However, they have a large assumption, which is that the quantum device is very good, so there is no noise at all. So all the things operate with the pure noiseless scenario. And also they assume they have a very large number of qubits, right? So maybe millions of qubits that we can use at hand. But actually those are not realistic back to 30 years ago because people are not fabricating any of the quantum device. So after 10 years, around 1995, people also start to realize that actually we don't have to fabricate the perfect quantum device because there is a theory called quantum error correction theory, which means that we don't have to fabricate those perfect qubits. We can just fabricate some good enough qubits, and then we can use the redundancy from a large number of qubits to build hierarchy of qubits, which means we can get the logical qubits from the physical ones that can correct some errors. So that gives us a very large confidence that we can just fabricate qubits as many as we want, as many as we can, and then we can use those qubits to build some to treat the redundancy for better reliability. And then in the last 20 years, driven by this concept, many of the research teams and also scientists from industry and also from academia, they try to build those new quantum devices and try to push the boundary of the number of qubits. So for example, Google is building this superconducting device, and also IBM, they are trying to build a larger and larger number of qubits, and also from USTC, they are building photonics ones, Xanadu, they are photonics quantum device. And with this recent progress in the quantum device, we are seeing some of the breakthroughs, like the utility demonstration and also the supremacy demonstrated by the Google quantum team. So those are some of the practical. So there is a question mark on the practical one, because we know that those algorithms may not have real applications, right? But we do know that if we have some of the quantum device that we can continue increase the size, at one day we can achieve the practical usage on those factorization algorithm or some other quantum simulation algorithm. So nowadays, 5 years later, after the demonstration of the quantum supremacy, right now the whole domain actually is having a agreement that we have to continue to push the boundary of this quantum error correction. Because we still need to make sure the quantum device not only have a large number of qubits, but also each qubits have to perform very well. For example, the error rate should be lower than 10 to the power of -8 to perform the meaningful RSA 256 of the factorization algorithm. All right, so that's basically the current status of the quantum device. A lot of the researchers are trying to demonstrate what is the best quantum error correction scheme. For example, the quantum alpha qubits paper from Google released yesterday is actually trying to do the error correction decoding process using the transformer models. And also some other researchers also trying to use the available device, because available device, they still have thousands of qubits, and whether we can find some meaningful application from the existing domains to do that. So that's the trend or roadmap to do the NISQ computing. So now let's step a little bit deeper into the basics of the quantum device. So just like in the classical device, we are using the bit to represent information. So you can have a 10-bit to represent 10 bit of information, either all zeros or all ones or some combinations of 1 and zeros. So the basic component of the quantum device is similar to the classical one conceptually, which is that we use the quantum bit to represent information. So we also call those quantum bit as qubit in short. So inside the qubits, you've been wondering what is the mathematical formation that we can describe the system of the qubits. So actually we are using a vector called state vector to describe all the information inside the quantum system. So just like imagine in a classical system, so now we are driving a car on the road, and then we want to tell another people, our friend, where is our location, right? So we can say, hey, we're at the location at the 100 mile on the highway. So that's like we can use a number to represent the state of our current location on a linear 1D system. So this is a very compact formation, so we can just use one number to represent all the information in terms of the location of the car. So, however, we can imagine we can also use another more redundant way to represent the location of our of the car. For example, we can say there are discrete, for example, in total 12 different locations, and then we can use a vector with a length of 12. And all the other numbers are just 0, and then we use one hot representation to say we're at the fourth place is only 1, and then all the other places are zeros. So we can also send this whole vector to our friend to say, hey, we are at this location. So that also represents all the information inside the system. So this is very inefficient. You can imagine originally we just need one decimal number, and right now we are using this 12 binary numbers. So, however, for the quantum device, actually this representation is pretty efficient, because in a quantum device, we are not the car can not only can be placing at one space, but also there is a probability of the car being at any of the locations. So there will be a combination of different locations, a superposition of the locations of the car on the whole road. So that's the magic or the special point of the quantum device. So which means with only one qubit, we can represent many different states, not only just a 0 or 1, but all the different combinations between the 0 state and also the 1 state. So more rigorously, we can use the qubit notation, the bracket notation, to represent the state of a qubit. So classically, we have either the bit in 0 or 1, but in the quantum, we can use this direct notation or the bracket notation. So for the 0 state, we are using the 1, 0, and for the 1 state, we can use the 0, 1 as the state. And for a very complicated state, for example, this Q0 is a superposition between the 1 and 0, so we can have the numbers on both this 0 state and also the 1 state. So in that case, we can imagine for 1 qubit, we are not only able to represent just 1 bit, but also 2 numbers, 2 complex numbers. So that has a much larger representation power compared to the classical bit. So we can also write this state in the form of the combination of the 2 basis states, right? So for example, the Q0 here can be square root of 2, 1 over square root 2 of the 0, and also plus I over square of 2 of the 1. So that means we have some of the energy of the system is sitting on the 0 state, and another part of the energy is on the 1 state. So this forms the superposition of the 2 basis states, which is a linear combination of those 2. So, however, when we actually doing some measurement or the observation of the qubits, we are still need to go back to classical one. So the qubits can stay there for a very long time, but in order to read the information from the qubits, we have to perform a process called measurement, right? So the measurement actually, for example, we can assign some microwave pulses to the qubits to retrieve the information, or we can take a picture of the qubits to see what is the state. So the important or the non-intuitive thing about the measurement is that when we actually measure the qubits there, the qubits will collapse to either a 0 or 1. So there is no way to directly measure the overall information, all the information of the qubits. And also during this measurement process, the collapse of the state will be randomly processed. So for example, if for the original state, this superposition between the 0 and 1, after we do the measurement, there will be some possibility that we get a 1 from the qubits, and also another possibility to get a 0 from that. So you may be wondering how can we on Earth to do some meaningful computation with the qubits? So the answer is that actually we can do the computation for many types, right? So say we can prepare the qubits for 100 times, and then we measure 100 times, and then you can get a distribution of the 1 state and also the 0 state. So in that case, you can obtain the meaningful results from the distribution of the classical state out of this quantum bit. So specifically, you've been wondering, what is the probability of this distribution? How can we know what will be the measuring results? What is the probability of measuring 0 or measuring 1? So mathematically, the probability to measure a 0 can be computed with this dot production. So basically, the x here is the state we just introduced, and also the phi psi here is actually the state we want to measure. So here we can use this x. For example, if we want to know what is the probability of measuring a 0, and then we can directly compute this process, which is the dot production between the 0 vector to the target vector, and then we can compute the norm 2 of this process. So for example, the combination process can looks like this. We can compute this overall value to around to 1 over 2, which means that when we measure this state inside this zero dimension, there will be half of the probability that we obtain a 0 state. And also, of course, there is another 50% of the probability that we measure the 1 state, right? So in that case, intuitively, the qubits that we prepared has half of the energy on the 1, and also another half of energy on 0, right? So in that case, when you do the measurement, the qubits must collapse to one of the discrete state, either a 0 or 1. And this process, this dot production, can help us to compute what will be the probability distribution for this measuring process. All right, so for the measurement process, there's actually one restriction, which is that when we measure the state in itself, for example, we want to measure psi here with itself, so the state must be 1 because the measuring state is the same as the state we are preparing. So in that case, we know that the dot production between the row vector of the psi to the column vector should be 1. And in that case, we know the two coefficient for those two eigenstates should be the norm 2 of them should add up to 1. So the alpha square to beta square should add up to 1. So as we mentioned, there will be an observer effect. So which means that when we measure the qubits, we know that with a probability that we obtain each of the eigenstates, either a 0 or 1. So the quantum state is called a collapsion to the classical state. So we don't know what is the exact state before we do the measurement. So that is very intriguing effect because, for example, if we know that there is a very famous this conceptual experiment which is called the Schrodinger's cat, right? So we are putting this Schrodinger cat in a box, and then there will be some of the item Geiger counter to count the number of items from this specific device. And then after a certain point, when you open the box, you know after a certain count of the counter, and then there will be a poison released to and then the cat will die. So, but before you open the box, you don't know whether the state of the box or the cat will be triggered, right? So that means when you do the observation, you decide what is the state of the current of the cat. So, but before you open the box, you don't know what is the state. So that is the superposition of the live or dead of the cat. So that's a very interesting mind experiments to do. So actually, that also observed in the real experiment. So in the qubits, after you prepare the state in the superposition, and then you do the measurement, you will see sometimes you measure 0, sometimes you measure 1, but you do have a distribution of the 0 and 1s during this process. Okay, so in order to have a very intuitive and also visual understanding of this, visual understanding of the state of the qubits, so we can also use another powerful tool, which is called the block sphere. So here, we know the mathematical representation for qubits is alpha 0 plus beta 1, and alpha, beta are the complex numbers. So we can also represent the beta as the EI phi beta with this polar representation. So in that case, we know we can change this complex number representation to the real number. So in that case, we have this alpha, beta, and also the phi. Those are the degree of the freedoms. And also we know because alpha square plus beta square, they also need to add up to 1. So in that case, we also further eliminate 1 degree of freedom. And that will constrain us, all the degree of freedom will be just 2 real numbers, which is the theta and also the phi. So we can actually represent the state of arbitrary qubits, single qubits on a sphere which is called a block sphere, right? So this degree of freedom will be theta, and also another will be phi. So we can see that any of this point on the sphere will be uniquely represented by one of the qubit state. So this is very useful for us to understand where is the qubits. For example, the north pole of this block sphere will be 0, and if we are applying a NOT gate, we are doing this revert of the 0 to 1. So that is essentially doing pulling this direction from this north pole to the south pole. So in the later slides, we will show how we can use this block sphere to better understand the operations on the qubits. So now we have this qubit state. We know that we can use the vectors to represent the state, and we also want to do some operations or the computations on the state. So one thing that is very different from the previous classical computation is that all the quantum gates are reversible. What is the meaning of that? So reversal means that after you do the computation, you get the results, right? And then from this operation and also the result, you're able to 100% to retrieve the original input state. So for example, if we are doing this NOT gate with 1 qubit, so say we want to do this flip of the 0 state to 1 state, and then because the NOT gate here represent in this matrix is actually a reversible gate, and then we know if the final result is 1, and then the original input will be 0. So that process is a reversible process. So one question for you is that what is the simplest reversible gate in a classical computation? So we know that the NOT gate and also a lot of others like the XOR or the C-NOT gates. So what will be the simplest one for the reversible gates in a classical computation based on the knowledge you learned? Any ideas?
Is it not 9?
It's not. It's simpler than NOT gate. Yeah.
Is identity?
Yeah, exactly. Yeah, exactly. So the simplest reversal gate is doing nothing, right? So it's just identity. It's mapping the input to output, right? So in that case, you know the input when you get an output because the identity gate doesn't change the state at all. So in that case, all the gates in the quantum actually are the reversible gates because we have to make sure the energy of the system stay the same as the original state. So reversible gates can all be represented as these matrices or the rotations around this block sphere. For example, the NOT gate can be represented with this 2x2 matrix, right? So for example, in this case, when we do the NOT gate on the quantum state, we can for example, starting with the quantum qubit 0 with the 0 state, and then we apply this NOT gate, and then the 0 will be flipped to 1. So in that case, the pointer will pointing to the south pole of this block sphere. So also, if we are applying this NOT gate to 1, we also rotate back this vector to the north pole, which is the 0 state. So besides this NOT gate, there are also other Pauli gates. For example, the Y gates and also the Z gates, right? So the Y gates is in the form of this 0 minus I at 0 state, and also the Z gate, which is 1 0 0 minus 1 gate. So basically, when we have this different basis gate, the X gate and also the Y gate and Z gate, we can have a look at what happens when we actually apply those gates to the different states. For example, if we are applying the Z gates to the 0 state, we know that after computation, we are still obtaining the 0 state, right? So if we are applying this Z gate to the 1 state, so what will happen? So finally, we get the -1. But physically, actually, the -1 vector is not distinguishable with the 1 state because the -1 here and 1 only different with this global -1. So when we do the global phase, actually that is called a global phase, which is cannot be measured during with the normal physical process. So in that case, we also consider that the Z gate applying to the 1 state will also be the same as the original state, right? So in that case, we know that the 0 and 1 are actually the eigenstate of the Z matrix because after we apply the Z, the original state will not change, right? So in that case, all the computation bases formed by the 0 and also 1 state are also called this Z basis computation basis. So we can imagine that also we have this some state that is stay the same after we applying the NOT gate, which is the X basis, right? For example, if the original state is the plus state, plus here, and then we can apply this X gate to the plus gate, and then we can see the final result will be still the same with the original one, and also that's also the case for the minus state. So in that case, we know that the basis gate of the X basis will be plus and minus, which is in the form of this one. And also similarly for the Y basis, we also have the left and right, which is this 0 plus I1 over square root of 2. So for the right and left states, so those are actually the several different poles on the block sphere. So for example, we know the 0 and 1 states are the north and south pole. And also for the plus and 1, they're actually the front one and also the back one. And for the right and left, they are the leftmost and also the rightmost pole for this block sphere. So in that case, you know what are the several anchor points on the block sphere that we can easily understand the gates when we have the understanding of these different locations on the block sphere. And then after this several poly gates, another very interesting gate is actually the Hanrui gates. So the Hanrui gates is actually a very different one from the classical ones, because starting from a classical state, which is the pure zero state, after applying this Hanrui gate, we are actually creating some superposition, right? For example, initially we can have this pure zero state, and then after applying the Hanrui gate, we are obtaining the plus gate, which is the superposition between the 0 and also 1. That's also the case for some other gates. For example, here we are introducing several of the very commonly used single qubit gates. For example, the phase gate, the S gate, and also the S dagger gate. The most general form of the single qubit gates can be represented with this U gate. Right, so here we have 3 parameters inside this U gate. So basically, when you're applying this U gate to any of the qubit state on the block sphere, you can perform the rotation from arbitrary location to another arbitrary location, as long as you configure those 3 parameters according to the computation you want to do. So in that case, the 3 parameter U gate is a universal transformation gate for a single qubit. All right, so in that case, in the second one, we basically introduced the single qubits and also how we can manipulate those gates. So just like in the classical computation, we are applying those NOT gates and also those C0 or XOR gates or XNOR gates. We have different kinds of gates inside the quantum device to manipulate the states of the quantum bits to perform the computations we want. All right, so in the second two, we are going to introduce multiple quantum bits. So because we know that we cannot just use 1 qubit or even 1 bit to compute any of the meaningful computations. So we have to perform the computations on multiple qubits. So here the interesting part comes that for 2 bits, actually we have the length of the vector will increase exponentially to the number of qubits, right? So for example, if we just have 2 qubits, and then the vector to represent all the possible state for the 2 qubits will be of the length of 2, of the length of 4, which means we have the energy on the 0, 0 state, 0, 1, 1, 0, and also all the way to 1, 1. So in that case, we have to represent n qubits with this 2 to the power of n of the vector. And also the normalization principle that we introduced, which means the two norm of all of the coefficient for each of the bases will add up to 1. So that still holds. So in that case, when we have n qubits, actually we have to use this 2 to the power of n of the complex amplitude in the state vector to represent all the state. So you can imagine that when we have 3 qubits, the size of the vector will be 2 to the power of 3, which is 8. And then if we have 10 qubits, and then the size of the vector will be 2 to the power of 10, which is over 1,000. So it is very difficult to simulate a large number of qubits, as you can imagine, because when we have 20 or even 50 qubits, and then the size of the vector that we have to store in the classical memory will be 2 to the power of 50. So that is too large to do the simulation. So that also gives us the advantage of us to store the information or do any computation in the quantum state. So here we can give an example for a complicated case, which is the collective state for 3 qubits. So basically, all of the qubits will adding this Hanrui gates we introduced in the first section, and then the collective state for the 3 qubits will be 1 to the 1 over square root of 8, and then there will be an equally distribution of energy and also the probability on all of the possible basis gate, which is all 8 ones here. So you may imagine, wondering what is the effect of the single qubit gates on a multiple qubit system, right? So what happens if we just apply 1 NOT gate on 1 NOT qubits in a 3 qubit system? So actually, when we're actually doing that, we can do this computation for a Kronecker product between multiple gates, right? For example, we have this Hanrui gates on the first qubit and also the NOT gate on the second qubit. In order to compute the overall effect of this H gate and also X gate, we can perform this Kronecker product between X matrix and also the Hanrui matrix. and we obtain this overall computation matrix in the size of the 4x4, and then we can compute what would be the final state after applying this 2 gates to 2 qubits. And also we have this joint unitary matrix, which means when we have this, for example, the NOT gate only on the qubit 1, which is similar to the previous case, we can also compute the canonical product between the X and also the I, and then we can obtain this 4x4 matrix for the multiple qubit system. So here I'm going to introduce one very interesting gate, which is the C0 gate. So C0 is actually the short for controlled NOT gate. The there are 2 qubits as input in this C0 gate. One is the input, one is the control qubits, another is the target qubits. So the control is the Q0 here, and also the target is Q1. So the control NOT means that when the original qubits, the control 1 qubits is 0, and then we don't do any computation on the target qubits. However, if we have a 1 on the Q0 here, and then we have to perform a NOT gate on the Q1, which is flip the state on the Q1. So in the middle here, we can see the truth table for this gate. So if the target and control are both 0, and then the output will be also 0, 0. However, if we are doing the control qubits will be 1, as in the second row here, and we know that the target qubits have to also be perform this flip operation. So the final output will be 1, 1, all the way to the bottom row, which is the input as 1, 1, and then we need to flip this target as the flip from 1 to 0. So the output will be 0, 1. So in that case, we can construct this truth table for the C0 case, right? So we can know that all the input are in the yellow representation, and also the output will be green. So when we actually input this 0, 0 state, and then the output will be also 0, 0. However, if I input this 1, 1 state, and then the output will be 1, 0 because of this flip of the target qubits. So in that case, we can imagine that the C0 actually performing a swap of those 2 states, right? So when we actually input this A state in this format, and then the output will be simply swap the location of this A11 coefficient and also the A01 coefficient as shown here. So how can the C0 gates create one very important concept in the quantum computing, which is the entanglement? Right? So imagine that if we are doing this Hadamard gates on the Q0, and then we can obtain this 0 plus state. So if we are performing this C0 gates to from the Q0 to Q1, after we apply this Hadamard gates on Q0, we can actually obtain a very interesting state, which is the superposition entanglement between the 2 qubits. Because the state here is actually 1 over square root 2 of the 0, 0 plus 1, 1. So what is the implication for that? So that means the 2 qubits are either all in the 0 state or in the 1 state, right? So for example, if you are preparing the state for 100 times, and then you measure that for 100 times, you can see that 50% of the times you obtain this 0, 0 state, and also another will be 1, 1 state. So let's imagine a very interesting scenario. So say I prepare this entangled pair of 2 qubits within the 0, 0 and 1, 1 state, and then I give one of the qubits to you, and you get on the starship, and then you can go to another side of the universe. And then you can measure the qubits, right? You measure qubits, and then you obtain, say, hey, we obtain a 0. And then if I also measure qubits at the same time, or just one second after you measure qubits, I will obtain the same state with your state, no matter how long is distance between us. So that is because 2 qubits is already entangled. So in that case, even the distance between those 2 qubits are far longer than the traveling distance of light in 1 second, we can still obtain the same result. Either you measure 0 and then I also measure 0, or you measure 1, and then in that case, my measuring result will also be 1. So that is called actually a spooky interaction in the distance. So which means somehow there seems to be some power that connecting those 2 qubits, and then if you measure this in one side of the universe, that also impact the result of another side, right? So In that case, you may ask whether we can do that using this entanglement between the two qubits to do some communication, right? So in that case, we can achieve this faster than light of the communication between two places, right? So, however, unfortunately, we cannot do any of the communication with this process. Actually, that's the non-communication theorem. So the reason for that is that, for example, you measure 1 on your side, and then actually you are not able to configure the qubits, right? So it's a purely random process. You just measure 1, and then I know I measure 1, but you cannot flip the qubits to communicate 1 bit of information because all the process is random. So in that case, the only thing we can guarantee is that the two states are the same, but we cannot send even if 1 bit of information through this process. So that is the non-communication theorem of the quantum communication. All right, so let's back to the entanglement here. So actually, besides this CNOT gates, there are also some other gates that can create some entanglement or performing this interaction between two qubits. For example, one gate is a CZ gate. So CZ means that we can use the Q0 to perform a Z gate, which is the Z gate we introduced in the first section to the second qubits. That is equivalent to perform a Hanrui gate first on the target qubits, and then perform a CNOT, and finally perform another Hanrui gate. And also we can perform a swap gate. So what is the meaning of swap? So say if I have something and then I can swap this to you, that means we can swap the information of two qubits, right? So swap means we can totally change the information of two qubits with those swap gates. And the swap can be also implemented or decomposed to 3 CNOT gates interleaved to each other. And also beside this swap gates, we also have the controlled rotation X gate and also many of the other CNOT gates, many of the other 2-qubit gates. So the control RX or the CRX actually is in the format at the bottom, which is that if we have this one state on the first qubits, and then we can perform this rotation X of the arbitrary degree on the target qubits. All right, so now yeah, please.
Oh, just a quick question, like how are the gates implemented in real life? Is it like a light frequency?
Mm-hmm. So that's a great question. So the actual implementation differs for different kinds of technology roadmap. So on the superconducting chip, for example, we are fabricating the artificial qubits, and then the gates is implemented with microwave pulses, microwave pulse signal. So we have this transmission line to the qubits, and then we can compute the shape for the pulse. And then the area under the shape will determine the rotation theta here, the angle here. So we can change the shape of the microwave to perform different gates on the superconducting qubits. And for another technology roadmap like neutral atom device, we are placing the neutral atom in a vacuum chamber, and then we use lasers to illuminate the items. And then we can determine the length of the laser, so how many seconds or microseconds we illuminate laser. So in that case, we also applying those gates to the actual qubits. So that differ based on different kinds of the technologies. Yeah. Any other questions? Okay, cool. So now we come to the third section, which is the quantum circuit. So the quantum circuit actually, now we already learned what are the qubits and also what are the basic gates on the qubits, right? So the next step will be construct a quantum program that we can do some meaningful computation, right? So we don't just want to manipulate one qubit, we want to manipulate a set of qubits to perform some meaningful computation and also obtain the result. So here we can firstly have a look at the overall component of a quantum circuit, right? So firstly, we have this initialization and also reset part of the qubits, where we want to initialize the qubit state with our problem formulation. For example, if we want to do some quantum machine learning task, and then we want to encode the information, say maybe it is an image or some of the sentence, we want to encode the embedding to the qubits. And then we want to apply some of the quantum gates, for example, the Hanrui gates or the CNOT gates, to perform the manipulation of the state. And then finally, we have the measurement of the qubits to obtain the final result. So that's like we can just like in the classical CPU, right? So in the CPU, you can fetch those different information from the DRAM to SRAM and then use ALU to perform the operations. And then finally, we need to we need to store those different computer results to the SRAM or to the cache as the final result. So that's also similar here. We need to initialize the qubits and then do the computation and then finally do the measurement. After the measurement, there actually can also be some of the classical post-processing of the qubits. For example, we can, based on the measurement outcome, we can do some classical controlled quantum gates here. So here, let's just have a very quick look at a very simple circuit, which is the adder circuit, right? So that is also I believe, the first class we learn in the digital circuit design, right? So we want to design an adder circuit. So what can we do in the classical digital circuit design, right? We can add those XOR gates, right? So because when we actually doing the adding of those two inputs, we have this truth table on the bottom right, and then for one of the bit, which we can directly use that as the flip this first bit, and then we can do the C0 of the Q0 to Q1 as shown on the bottom left. Right, so in that case, we can create this quantum circuit, which is basically performing this adder circuit. So what happens if we also want to perform this half adder? Now we have this half adder, right? So what happens if we also want to perform this full adder, which means we have to calculate this carry bit, right? So in that case, we can also use this multi-controlled C0 to based on the state of the Q0 and Q1 to flip the Q3. Right. So for example, if we are inputting either of the Q0 or Q1 is a 1, and then we know the carry bit should be also 1. In that case, we can obtain this number on Q3. But if all of the Q0 or the Q1 are the 0, and then we don't have to perform any of the flip on the Q3. So in that case, we can see the basic operation yeah, please.
Why do you need the C0 gates? Because is it like what do the green boxes need? Because I know the blues are the C0s, but do you need the green boxes to properly add?
So you mean the first the state here?
Yeah. What is that? What is that?
Okay. So let me see.
Is that the initial state?
Yeah. So here is the initial state to. You can see the two separation line here, right? So the first one is the initial state that we want to add a 1 to a 1, right? So in that case, we need to perform an X gate to perform the initial state preparation. Yes. So and then all the calculation in the middle between two dashed lines are the full adder we are using, and then for the two measurement we obtain the final result.
Okay, thank you.
Okay. So that is the basic process of the full adder. So here we can have a look at a very quick example of a very simple quantum machine learning circuit, right? So for example, if I want to do some NISQ classification, so in that case, the first thing we need to do is to encode the NISQ image to the quantum bit. So there are many of the process to encode the classical state to the quantum bit. So here we are just using a very simple one, which is the phase encoder, which means we are encoding those values of the pixels. So here you can roughly see there's a downsampled number 2, right? So in that case, we can use this 4x4 image, and then we have the pixel values for each of the pixel here in the grayscale, and then we can encode the value of the pixel grayscale number to the rotation angles for those different rotation gates. Right, so here we can use a 4x4 of the array of the encoding process, but also there are many of the other encoders that we can use. Some of them are using this amplitude encoding, which means you directly encode the state of the image to the qubit state, or you can use this binary input where you can basically just use this large number of qubits, and each of them is either 1 or 0. So there are many ongoing research to trying to find what is the best encoding process to encode the classical state to the quantum state. So after that, we can also have this trainable quantum layers in the middle, in the color of the gray and also yellow. So those values, those are the U3 gates and also the controlled U3 gates. right? So those gates actually can perform the desired manipulation of the input state. For example, you can train those values based on this back propagation process to make sure that the state you are performing on is actually the final state you are doing the computation represents some of the unique aspect or unique information about the number or the digit that we are in the input image, right? So in that case, after this computation or manipulation of the input state, we can finally do a measurement. So to the measurement, we can obtain the 4 numbers, right? So imagine if we are just doing, say, 4-digit classification, we can simply do some post-processing, maybe just adding 1 softmax as the post-processing, and then we can obtain the values for each of the digits here. So that is a basic workflow of the quantum machine learning process. So we have this encoder to encode the class of input, and then we have different layers of the quantum device to perform the manipulation. Yeah, question?
What happens if your input dimensions don't match the output ones? You just have more qubits.
Mm-hmm.
How do you make it match up?
Yeah, so the question is what happens if the output dimension is different from the input or the number of classes we want to classify, right? So the answer is that actually the post-processing here, one thing is that we can perform the measurement on many different bases. Right here you can see we are just measuring on the all Z basis, right? So we can also measure on the, for example, all X basis or XZ basis. So the actual number we can obtain from this 4 qubits is at least 2 to the power of 4, which is 16 numbers. So in that case, we can later on adding a post-processing like a fully connected layer to classify as 10 class or like a larger number of classes. So the important thing is that we can doing different measurement to obtain the information from the quantum device, and then we can add in one more layer of the final post-processing to match the dimension of the information we have to the number of class we want to classify. Okay, other questions?
Yeah, let's say your input image is like 555. Does that mean you have 5 qubits with like RX, RY, RZ, RX, RY? Like you just keep repeating that?
Mm-hmm.
Or do you have to do something else to encode it in that case?
Yeah, so the question is what happens if we have a 5x5 image? Yeah, that's a great question. So actually, if we have a 5x5, so the encoder here, first of all, is actually only one example. So there are tons of different kinds of encoder. So the quick answer is that we can just add in one more qubit, right? And then we can encode the 5x5 gate to this. Or we can also use like maybe 25 qubits, right? And then we can just add in one gate to each of the qubits to encode the state. So it's just like the neural architecture search in the classical machine learning. In the first layer, you can use a 3x3 convolution. We can also use a 5x5, right? We can even do a flatten of the input image and then just adding the fully connected layers, or we can use transformer models. So there's a tons of probability or a very large design space to encode the information to the quantum gates. But inside in this scheme, typically we can just increase the size to 5x5 to store the information. Yeah. Cool. All right. Okay, so this is a very basic scheme for the quantum machine learning circuit. So basically, we have this idea of how we can use the qubits, right? And also how we can construct a circuit to compute the meaningful result obtaining from a quantum state. So you can imagine that actually for this quantum circuit, imagine that we have a very large input, right? For example, very long documents for long context learning. So in the classical device, we are suffering about this quadratic increasing of the attention if we're using the transfer models. So however, on the quantum side, we can easily use relatively the logarithmic number of the qubits to encode the very long context. Because with this 4 qubits, we can store the 2 to the power 4 of the information. And with say 100 qubits, we have extremely large space, right? So you can imagine if we are able to find a very efficient way to encode the information to the quantum state, and then the processing power will be very large. And also the number of qubits required is a very small number compared to the classical device. However, in order to encode the information to the quantum state, actually there is a large difficulty. So typically, in order to encode the state very accurately to the quantum state, you also need to pay the cost of the exponential deep of the encoding circuit, right? Because typically all the qubits are initially to the all zero state, and then if we want to if we want to encode to an arbitrary state, and then the gate number of gates you have to apply in the initialization stage is also very large. So that's actually the current bottleneck, or one of the challenge for the quantum machine learning community is the data encoding or data uploading process. How can we efficiently represent the state in a quantum device with a very small cost? So that's an ongoing research efforts to trying to reduce this cost and also like fully leverage the available number of qubits. All right, so now we have the idea about on the algorithm side, what we can do to manipulate the state of the quantum bits, and also what are the gates we can perform, and also what are the quantum machine learning basic models. And on the device side, we are going to just introduce some basic idea of this noise intermediate scale quantum era. So as you know, in the machine learning community, people also want to, for example, classify this different several different train of the deep learning or machine learning. And currently we are staying in the third train of the machine learning, right? So that's also the case in the quantum. So we are actually have several large waves for quantum, and right now we are actually in this NISQ era. So NISQ means that we have a noisy qubits. So that means the quantum bits are very sensitive to the environment. So when we actually doing the computation on a classical device, for example, you are open the laptop and then you're just using this 1 + 1, and then you you enter the equation you want to compute, and then 100% of the time you obtain a correct answer. However, if you are doing this on a quantum device, right? So you are doing this full adder on a quantum device, 1 + 1, as we just introduced in the last section. There will be a pretty large non-significant probability that we obtain a wrong answer. That is all because of the noise on the quantum device. Because all of the operations, like the NOT gate and also the CNOT gate, cannot be faithfully implemented because of all kinds of noise. For example, the control wave, the microwave pulses are not this perfect shape, and also there are some interactions between the qubits to the environment, and sometimes the cosmic ray from the universe, and also some from the sun, they also will impact state of the qubits. So it's a very vulnerable and also very fragile process to compute on the qubits. So that's why we are calling this a noisy process, right? So typically you can see that the error rate for the single qubit polygates, they are on the range of the 10 to the power of -3, and also for the CNOT they are 10 to the power of -2. So that means when you compute 100 times of 1 + 1 on the quantum device, you will get one wrong answer, right? So that is actually not very good result, because we want to, when we actually do a more complicated communication, say you want to execute some quantum machine models, so there will be tens or thousands of gates or even millions of gates, and then if the device is not reliable enough, and then the result will be also not correct. And also besides this noisy, we also have limited number of qubits, right? So typically we have tens to hundreds or up to several thousands of qubits in the available device. And also we have a limited connectivity between the qubits. So here is a figure for the IBM Washington device. For example, we had this brick like the shape of the quantum bits. So it is called a heavy hexagon, because on each of the ring here, there are 12 qubits, and also there's 6 vertices, and also there will be 1 additional qubits on each of the edge. So it's called a heavy hexagon topology for the IBM device. So right now, if we are placing those available devices from superconducting IBM, Google, and also triple ion, those IonQ continuum devices on this 2-dimension grid, we can see one dimension is the system size, and also another dimension is the error tolerance, right? So we can see it's better to have a very large device and also have a very large error tolerance on the top right corner. However, we can see on the top right corner, there are actually the requirements for several quantum algorithms. So one of them is the Shor's algorithm to do the large number of factoring, and also the Grover search for the structured database search, and also several others for quantum chemistry tasks. We can see that there is still a pretty large gap between the available devices and also the requirements from the hardware side, right? So our idea is that whether we can do some computation, especially for our from the computer system background and also the computer architecture background, how can we do some of the optimization on the middle layer to close this gap, right? So, for example, one of the very important tasks and also one thing that we can contribute from not only the device but also the CIS computer system side is that we can do the qubit mapping process to choose those good qubits to start with, right? So, for example, in the IBM device here, we have 127 qubits, but not all of the qubits are created equal, right? You can see that some of qubits have a darker color, and some others, they have a lighter color. So that actually indicates the error rate for each qubit. So one very intuitive way is that we can just choose those very good qubits, right? We can choose those qubits with very high reliability of the operation to do the computations. So that's also the case for all the intuition behind this qubit mapping process. But also there is another difficulty. So for example, here we have 4 qubits, Q0 all the way to Q3, and we have the topology on the right-hand side. So if we want to do the first gate, which is in this red dashed line, we can simply perform a direct interaction between the P0 physical qubit 0 and P1 physical qubit 1. However, if we want to perform this gate between the Q0 and Q3, right? So you can see that the P0 and P3, they are not directly connected to each other. So in that case, there is no direct direct gate that can be performed between those 2 qubits. So what we can do is that we can perform a swap case between the P0 and P1, P0 and P2, right? So we can swap the information of the P0 and also P2, right? So after this swap case, you can see that the P0 right now is locating in the center of the grid, and that has a direct connection to the P3 on the top right corner. In that case, we can later on apply this direct case between the P0 and P3 to finish the computation according to the quantum program on the left-hand side. So you can imagine that in this process, we are adding one additional case, which is the swap case between the P2 and P0. So how can we actually reduce this overhead? So you can imagine that because of the large error rate, every swap gate we insert to the system, we also introduce a large error, right? So in that case, we want to minimize the error that we introduce to the whole system, right? So that is actually one of the very widely studied topic. So how can we reduce this swap insertion overhead during the qubit mapping process? So here I'm going to introduce this one example, which is called a Sudbury qubit mapping process, which is also used in the IBM Qiskit framework, right? So basically the idea behind this is that we can have a look at all of the swap candidates, right? So we can see, for example, we can do the swap for the P0, P2, and also P0, P1. So there are 6 available swap in the candidate list. And then we can see each of them to see what happened if we perform the swap between those 2. And then there will be a H, which is a heuristic function to compute the score for the topology after this. For example, if after this swap case, there are many of the direct gates can be computed, and then we have a high score for that swap. Right, so we can do this to compute the swap for the score for each swap case. And then finally, we can find the swap case with the minimum score to perform the swap. And then we can perform that at the end of this compilation process. And then with this, there is an interesting heuristic also to do this. Firstly, with this initial mapping, right, we can perform the swap insertion case, and then we can obtain the final mapping. And because all of the quantum circuit, they are reversible, right? So the heuristic here is that we can just reverse the original circuit, and then we can do the mapping from the start, and then we can all the way go into the initial one, right? So which is the updated initial mapping. So in that case, we can update the initial mapping and then do the compilation to the end, and then to the reverse one to go all the way to the first. So in that case, it's like bootstrap process to always improving the initial mapping of this process. And then we can always have found a way to reduce the number of swaps we have to insert to this system. So this is the heuristic-based qubit mapping process. And later on, we also introduced the quantum NAS framework, which we developed in our lab, which is actually basically trying to use some of the machine learning-based method, like the evolutionary search or the Bayesian optimization or reinforcement learning to find the best initial mapping. So the basic idea is that we have this evolutionary search engine on the left-hand side, and then we can generate a lot of the initial mapping candidates and compute what are the actual overhead on the real device, and then we can provide the feedback to the original search engine. All right, so finally, I'm going to introduce a very simple example on the neutral item device compiler. So as we introduce and also the questions we discussed, we have the superconducting device, and also another very popular device that we have on hand is actually the neutral item device. So for the superconducting ones, a neutral item, and also some triplet ion device, we actually can just access them on the Amazon Web Service or Microsoft Azure. So you can just log in to AWS, and then you can just directly access to those quantum devices to play with. So for the neutral item device, we can see the number of qubits increasement is also very significant, right? So back to around 15 years ago, we have 2 qubits demonstrated, and then last year or this year, the start of this year, there's already been over 60,000 of qubits demonstrated by the Caltech team. So in the neutral item device, we are actually placing all of the item inside this vacuum chamber, right? So we are placing those items in this 2D grid, and then we can do some illumination of the laser to those items to perform the necessary gates. So this kind of device is important. Is very important because several aspects. First one is because all of the qubits are just items, right? So the items are prepared by the mother nature, so all of them are identical to each other. So also they have a very long qubit lifetime compared to the superconducting. They typically have 10 seconds, which is around like 1,000 times longer of the qubit lifetime. And also within a very small area, 1 millimeter square, we can fit over 10,000 of qubits. So here, inside this quantum device, this neutral item device, we actually have different types of the qubits array. One type of the array is controlled by this spatial light modulator, or called SLM lasers, right? So basically, we have this laser to create this light pattern, and then we can place those different items on this grid. And during the computation of the whole process, we cannot change the locations of those items. And also there is another very interesting kind of the neutral item array, which is called this movable item array, right? So the movable item array means that when we actually change the locations of the lasers, and then those items staying on the crossings of the grid will also change the corresponding locations. So in that case, you can imagine that the topology of this neutral item device is actually pretty flexible, right? For example, we can perform the movement of those items during the computation, and then there will be some new pairs of the items can be performing this eligible 2-qubit gates, right? So here we are showing that all of the qubits within a certain range of the distance, which is called Rayburn radius, can perform the eligible gates. So in that case, you can imagine that that gives us a very large design space to start with, but also some of the challenge to perform the compilation. So here, one of the framework is the atomic framework, which for this kind of device. So the goal of this framework is that we can provide a software framework to decide which item to use to start with, and also schedule the movement, and also provide this insight and also guidance for the future device, right? So because we want to understand what is the best mapping between the items to the specific locations, and also what is the scheduling of the movement of those lasers during execution. So here I'm going to give a working example. So basically the circuit on the top is the quantum circuit we want to execute, right? So in that case, we firstly map those items to the corresponding locations, and then we can move those items to the corresponding positions And then because we want to perform the gates between the Q0 and Q1, and also Q2 and Q3, so in that case, we can directly illuminate the global laser to perform all the gates between them. Right? So in the second step, we can also perform the illumination of those two gates. So all the gates within those distance, the pair of the 1 and 2, and also pair of 5 and 7, they have to perform this gates altogether. So in that case, we can perform this the movement for each step until we finish all of the gates indicated by the quantum circuit. So this is the basic compiling process for the neutral atom device. So there is also some of the recent progress on this device to trying to minimize the swap gates that have to insert during this process. So the basic intuition is that for all of the qubits, all of the items inside those arrays, so if we have a look at the one array here, for example, the blue one on the top left corner, we know that we can always perform the movement of other arrays to make sure any atom in another array can be very close to this one. So in that case, we can formulate this coupling map of this device as a complete multi-parted graph. So the reason for this is that for any of the atom pairs, as long as they are in different subgraphs, we can always perform a computation between them because we can always perform the movement, right? So in that case, one of the strategy to reduce the swap overhead is to directly construct those 2Q gates frequency graph, and then we can find the max k cut of the graph, so that we can find the separation of those qubits to different subgraphs, right? So that is one of the compiler optimization we can perform to make sure we can reduce the overall number of swaps we have to insert to the compilation process. All right. So we also have several other optimizations, for example, how to perform the mapping inside this process, and also how to perform the scheduling. But here I'm going to skip this. So the basic intuition is that we can always perform this part by part. For example, we can firstly find the gates in the front side and then do the compilation for this process and then to illuminate the lasers, and then we can do this process for multiple times to make sure we can finish all the compilation gate compilations. Okay, so here I'm going to just briefly show the result compared to the previous work. So basically, there are some works on this compiler trying to formulate all of the compilation process as the SMT solver SMT problem, and then they can use a SMT solver to find the optimal solution. So you can imagine the SMT solver can always provide the optimal solution, but the difficulty for that is not able to scale to a large number of qubits because of the exponential cost of the SMT solver. So in that case, compared to the solver-based method, the compiler here, the atomic, can always be very scalable. So basically, for a large number of qubits, over 1,000 qubits, we can also use this compiler within the 260 seconds of compilation time. We can find a feasible solution to run on the available device. So this is very important because imagine that we already have access to those large devices. So we need to find this very specific compilation process for us to run those different compilation and also different algorithms on this device. And also here, the compiler here can also provide the guidance for the movement speed. So basically, we can say what is the time per movement, and also analyze the error rate for each of them. So in that case, we are able to provide this very important insight and also the guidance for the future development of the neutral atom device. Okay, so this is the overview of the compiler process for the neutral atom device, which is another very popular available device nowadays. All right, in summary, in this lecture, we introduced some basics of the quantum device to give you a big picture of how can we copy and manipulate those devices and also qubits. We introduced the single qubit gates and also multiple qubit gates to manipulate this large exponential size qubit space. And also we introduced a quantum circuit to perform the adder process and also the quantum machine learning circuit. And also we introduced the NISQ era, which is the current era and also the compilation for the superconducting device. And finally, we also give an example for the neutral atom compiler. And in the next lecture, we'll also continue our introduction of the quantum machine learning. So we'll introduce more advanced models of the quantum machine learning, and also how can we incorporate the noise of the real device to improve the robustness and also scalability of the quantum machine learning models. So with that, thank you very much for the attention. I'm happy to take any questions. Thank you. Yeah, question?
Do you have any influence over how companies like Google and IBM design their quantum computers, or do you just have to kind of deal with their designs and adapt your algorithms accordingly?
So your question is what is the specific process they fabricate the device?
Oh no, I mean like, does your work influence how Google and IBM design the connections between their qubits, or do they just do it and you have to kind of like live with it? And
Okay, so one of our work actually influenced the software stack of IBM. So basically, they try to, for example, after they fabricate a device, and then they need to have a software framework to do the compilation. So one of our compiler is actually one of the default process or the ecosystem process in the IBM device to do the quantum machine learning process. So, and for the device, we do have some of the work, and also the community have some work to do some co-design of the device to the quantum algorithm, right? So I think right now the IBM device is still mainly the same strategy as they fabricated in the first place. So they didn't change much of the heavy hexagon device. But I think in the future, we do have a lot of work to try to implement the quantum error correction code on the device. So in that case, we propose some of the best topology of the device to implement those code according to the structure of the error correction code, the checkings, and also the interactions. And I think in the future, the device must be co-designed with the error correction code to implement the most efficient error correction fault tolerant computing. Yeah. I think there's a question there. And also for the Google, they have this alpha qubit paper, right? So they are using the transformer-based models. So actually before that, we also have a paper which is transformer QEC. So actually we also propose this transformer-based decoder for the surface code. So I think we have also this influence on the algorithm side. So how they design this decoder part. So I think for the hardware side is so we try to find some more impactful way to collaborate with them. So one example is we collaborate with Dr. Will Oliver's group here. So we try to do the placement of the qubits with some of the automated process. And then we try to, in the future, we try to have some possible tape out of the qubits. That will be like a fully automated design with the machine learning method.